Alrighty, folks. So we've gotten a chance to talk about Newton's laws and to talk about forces. Now let's take a moment to look at the formula or formulas for this chapter. There's really one important one and sort of a secondary one that really complements the first one. So, if we were to consider Newton's second law and what it tells us, Newton's second law tells us that the acceleration of an object is proportional to the net force upon the object and inversely proportional to the mass of the object. Now, if we take those words and turn them into an equation, it looks like this. The acceleration is directly proportional to F. That is, the F is on top of the other side of the equation. If the F increases, it causes A to increase. And inversely proportional to the mass. So the mass is on the other side of the equation, but on the bottom. So if the mass were to increase, it would decrease the acceleration. Now, this relationship, the type of relationship between A and F, directly proportional, and the type of relationship between A and M, inversely proportional, these types of relationships will show up again and again in physics and in math. And we will talk about them throughout this whole semester. We will see what types of variables are proportional or inversely proportional to each other. It's sort of a fundamental relationship between them. All right, well, this defines acceleration based on force and mass, but it's not usually how Newton's second law is written. Newton's second law is typically written as F net equals ma, that the net force is equal to mass times acceleration. And Newton's second law is probably the most important equation in all of physics. It's one of those situations kind of like the debate between Michael Jordan and LeBron James. You're probably never going to come to an agreement as to what is truly the most important, but this is certainly one of the all-time greats when it comes to physics. And let's talk a little bit more about it. So, for instance, we saw back in Chapter 2 that displacement was a vector, and when we defined velocity from displacement, that meant velocity was a vector. And then we defined acceleration from velocity. And so acceleration inherited that vector nature from velocity as well. Well, let's take that one step further. We now see that F is defined by A, force is defined by acceleration. So if acceleration is a vector, that means force is also a vector. And that shouldn't be too surprising. A vector just means that direction matters. And certainly the direction in which you apply a force to something is going to affect what happens. You push something upwards, it moves upwards. You push something downwards, it moves downwards, and so on. Which direction you apply the force is going to help determine what direction the resulting acceleration will be in. All right, well, we defined this with F net. So let's talk a little bit more about F net and what that means. Net in this sense really just means left over or all together. And mathematically, F net is defined as the sum of F. This is capital sigma, the Greek letter sigma, and it means summation, which is just add them all up. So F net is really just all of the forces added together. F1 plus F2 plus F3 plus whatever else is in the problem. There might be no forces, there might be millions of forces. We're not going to deal with millions of forces in any problems that we study. Maybe 3 or 4 in the most complicated situations. But nonetheless, however many forces there are, you simply add them all together, and that gives you your net force. All right, now let's talk about the units of force. Well, we've already got something new to talk about within the definition for force, and that's mass. We use the lowercase letter m to indicate mass, and the units we will use for mass are kilograms. The other piece of force is acceleration, and we should be quite familiar with acceleration after last chapter. The acceleration has units of meters per second squared. So if we put this all together, the units of F should be the units of m times the units of A. That is kilogram times meter per second squared. Kilogram meter per second squared. Now that's kind of a mouthful, so we have a special derived unit, the Newton. 1 Newton is 1 kilogram meter per second squared. And it's named after Sir Isaac Newton himself, and it's abbreviated with the capital letter N. Now, you are probably more familiar with the British unit for force, which is the pound. Pounds are what we are used to measuring force, the unit we are used to measuring force with. And to give you a quick reference here, I have the conversion listed for you. 1 pound is 4.5 newtons. Now, if you were to divide each of those by 4, you'd have 1/4 of a pound and about 1 newton, a little more than 1 newton. So to help you guys remember this relationship, I give you a silly challenge. I challenge you to go to McDonald's and try to order a Newton burger. Now, if your cashier has had physics, they might be clever enough to just ring you up a 1/4 pounder, but more than likely they're going to give you a blank stare and ask you to repeat your order for them. So hopefully with that silly idea in mind, you can remember roughly how to approximate newtons in pounds if you want to, ask yourself if an answer is reasonable. Working back to units you're more familiar with will probably be a better idea. That way, if I tell you I weigh 200 newtons, you can decide whether or not that's a reasonable value. All right, well, that's it when it comes to formulas. We really don't have many this semester. This chapter. But the one we have, Newton's second law, is a Swiss Army knife of an equation. We can use this in so many ways, and we'll look at a lot of those when we go to work examples later on. So it's what I like to call deceptively simple. F equals ma, but it's really F net, and the devil is in the details. So we'll get to see that later on. For now, let's just commit this to memory. You will use this again and again and again this chapter, and it can be applied to so many other things. So we'll pause there, and we'll come back and get a little more deep into gravity. We're going to take a deeper look at the force of gravity in our next video.